Hello everyone, this is the video lecture for Calculus 1, Section 5.3, the Fundamental Theorem of Calculus. Calculus. We're still stuck in math prison. I think this might be the last section of it. It's just hard to not actually do what we should be doing. Now, there are a couple interesting things that come up in this section, and that's fine. I'll explain them when we get there. But on the whole scale of things, a lot of this is not stuff that you'll be doing every day in the rest of your calculus career. But there are a few good questions in here still, and I think the next section finally we can kind of have a little bit of freedom to do what we need to do. Sadly, though, the very first question that you have on your homework is this ridiculous problem. This is sadistic. It's terrible. This should not be the first problem on your homework. I made a small mistake. There's a comma here instead of this. Okay. This should not be the first question on your homework. But I'm going to do it because it's the first question that comes up. So I'm going to do it faithfully. Trying to be faithful at least. We have our h of x is equal to this integral, and they say find the derivative. Well, so the integral is an antiderivative, right? And so they should cancel out one another. Basically, I'm saying find the derivative of my integral blah, blah, blah dx, and you should be left with the blah, 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 okay? Because all of this will cancel out. You integrate, and then you take a derivative. It's kind of like you're adding 1 to the power, divide by new power. Oh, wait, never mind, bring the power back down to the front and minus 1 from the power. And it just basically disintegrates. Here, let me just actually do it in a real problem here. So yeah, we got x squared. And so I'm going to integrate. This is integrate. And so then I've got add 1 to the power, divide by new power. But then I need to take a derivative of that. And so the 3 is going to come down to the front. I minus 1 from the power. And notice that the 3's cancel. We're back to the original. That's exactly what's going on in this very problem. And so, what is your answer? It's going to be 3 ln of t. Almost, but not quite. And it's not. It's just the little things like that. Okay. Yes, this will apply. This style here that I just said, it will apply to 90% of the other problems that look like this. We're going to see one here in just a few minutes. But not number 1. Not the first one on your homework. There's no consistency here. I'm not angry. I'm just telling you as it is. So here's the style. Here's the process in order to go and find your h prime. So I need to take the derivative of that integral, okay? I'm showing you the process. That way we can all get through this, okay? If you don't like me being this way, well, there's other videos, I'm sure. I mean, I like you guys, but I'm going to be my own guy, okay? So, I'm taking the derivative of my integral. What they want you to do is set the top to a u. Okay, set the top to a u. And so what happens is that we have u is equal to e to the x. And we'll get more specific on that here in just a second. But in order to do all of this, I'm going to change any x that I see here. Oh, well, I'm not going to change it. Yeah, I will change it. Nah, I'm not going to change it. Let me go more slowly. My notes, I've skipped a couple steps, but, it's fine. So, okay, we got this guy here. Cool. Everyone's happy. Well, now I'm going to multiply it by du over du because, of course, that's what we're supposed to do. And so I changed my e to a u, and I'm going to multiply by du over du. I'm going to exchange these two. Actually, it looks basically the same thing, just as a du there. And in just a second, there'll be a dx over here. Okay. Um, cool. That was so much fun, and we're definitely not done anywhere near done. Sorry, that T just didn't look good enough to me. And so next, I actually need to integrate. Okay, I need to integrate, and also take the derivative kind of like all at once. Like I was saying up here, it's just the inside part. And so what actually happens, and this is kind of strange, all of this right here is going to change into 3 ln of u. All right, so all of this changed into this, and then, but we still have this thing, du dx. Well, this is an interesting thing right here because what this really is u prime. See, we had a u, so what's u prime? What's your derivative of e to the x? It's e to the x. And so then now we say ln of u times e to the x. Well, now we're mixing up our u's and our x's. Can't I replace this u? Yes, I can replace it with an e to the x. Oh my goodness. Oh, and ln and e, they cancel. Oh my goodness. And so this is actually your answer that they want for this problem. Now, I think the biggest leap is taking it from here, taking here and moving it down to this. But the essential fact of the matter is that I'm taking the derivative of the integral. So in a wild math sense, this is not bad math. This is a wild normal math, I guess. I'm just getting rid of all this and leaving this behind. Of course, with a u instead. There are a couple other steps in there. I'm not going to go into each one of those, but essentially, if you integrate this guy, then it'll happen. Now, I'm gonna ask you the question: why don't I just integrate this? Why don't I show you what the integral of ln of x actually is? Well, do you know what that is? You don't? That's not like one of those common things that you know and everybody already knows. I don't know it. I mean, I know kind of what to look for, but I can't remember the formula for that. It's okay. It's okay. This happens, and you just put that in, and we keep moving, okay? So it's going to be great. Now, the only stipulation to any of these problems is that this right here must yield a 0, okay? Like, when you plug in the 1, ln of 1 makes a 0. Very good. And so what's going on here, in reality, is it's 3 ln of u minus 3 ln of 1, kinda. I don't really, I'm not going to support this view entirely, but the basic idea is that goes away, okay? That's not great math, but it's good enough. This is good math. This is, And then I have a little note here. It says, crazy first problem. I don't make up your homework. I'm just doing it with you, okay? We're just working through it together, and I'm not doing all the homework problems. I would love to, though, but just time's sake, education's sake. Got to be a good teacher once in a while and let you do your work, and that's okay. But you can always ask me questions. Hey, Chad, what are we supposed to do on this problem? And I'll say, you got to do this. Okay, so finally, it's like I'm going back to the car analogy again. We're finally able to get the keys to the car, but our parents say, okay, well, just as long as you're just going around the neighborhood, and that's okay, then you can go ahead and do whatever you got to do. Okay, so we're gonna go drive to our friend's house, and it'll be fine. And that's one of these problems. I know that it looks a little bit more difficult, just maybe because we're finally by ourselves and we could finally do this all on our own. But it's actually not that hard because what we're going to do is add 1 to the power and divide by the new power. And so the 4/5 stays in the front, add 1 to the power, divide by the new power. The 3/4 stay in the front, add 1 to the power, divide by the new power. The 2/5 stays in the front, add 1 to the power, divide by the new power. And we're going from 0 to 4. And so then you're going to plug in the 4 everywhere. And then you're going to plug in the 0. But what happens when you plug in a 0 everywhere? I'll wait for it. It's all 0. This wasn't looking good. I thought I could make it look good. It didn't look good. That's a 4 there, sorry. Okay. So yeah, if you plug in the 0, you're just going to yield a 0. And so essentially you could just ignore that. This is all in the stipulation that I can actually write properly. And so again, I'm basically saying all this stuff, just to be proper, minus 0 plus 0. There you go. So yeah, 0. And you put all this stuff together in your calculator, and you get a 192 over 5, and there you go. Next problem. Whew, finally we can actually do some real fun math here. This is going to be fun math. So, you go over to your friend's house with the car, and they're like, oh man, you got the car all by yourself, let's go driving. And so your friend says for you to go drive down a very twisty mountain road. I love these analogies. Do you need to know how the engine is working at this point, or how the radiator is cooling off the components and the timing belt is giving the pistons the... No! You don't need to know any of that. We're just here driving. It's a little bit twisty, but that's just part of the ride here. I got to stop that analogy at some point. So, how do we do this problem? And how do we do this problem in Calculus 1? And so later on there might be other ways, but I really suggest keeping it simple in any calculus class. What I'm going to do is I'm going to split up my denominator. I'm going to distribute my denominator. Okay, both of them get that denominator. It's kind of like the opposite of common denominator. Okay, something like that. They both have that in the bottom. And so then I've got this weird thing and this thing. Now what do I do? Well, let's just make them easier to integrate. And this is a very key goal that you'll be using very often as you keep going through the calculus classes. Notice that that's a 1/2 power, right? The square root's a 1/2 power, but it's in the denominator. And so that makes it a negative 1/2 power. And I write it up like this, okay? Also, you do not have to do it this way. I don't recommend doing this in the end, but you could split up your integrals right now, and it's no problem. I normally don't do it because we imply doing it anyways. Notice that we got an x squared, and then we got this negative 1/2. And so we got x squared times a negative 1/2, and multiplying their bases are going to be adding their powers. So 2 plus a negative 1/2, 2 minus a half, is 3/2. The 6 can come to the front, and you integrate. So what I'm going to do is I'm going to add 1 to the power, and I'm going to divide by that new power. Okay? That's not a hard trick. I'm going to add 1 to the power and divide by that new power. And so this should end up being a 1/2 and a 1/2. And there's a 5/2 and a 5/2. And now we just want to make it look pretty. And so this 1/2 and the 5/2, they're technically in the numerator flipped. And so that makes a 12. 2 times 6 is 12. X to the 1/2. And then here we got a 2/5. X to the 5/2. And so I plug in the 4. I'm going to plug in the 1 here in a second. Notice that I'm not even reverting back to square roots and stuff, because you should be using a calculator to do this. Plugging in the 1. It's not hard to use a calculator. Even if it looks a little crazy like this, a lot of it can be simplified. 1 to any power is just a 1, so you don't need those things. I guess you could say that's a 2, and you could probably do some math on that one. Blah, 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 and we get our answer, and we're done. So that was actually a really cool problem. Some of these are actually good for us. Some of these are actually what you will be seeing in the future. Now, this one's just a strange problem here, honestly. And so, x to the e power, and then e to the x power. It's very weird. Yeah, I don't know what this is, but it's okay. We're going to figure this thing out. It's not hard. It's just weird. And so this is x to a power. Let's just say that was a 2, because it's like 2.7 or whatever. Let's just say it's 2. So what would you do if it were a 2? You would add 1 to the power and divide by the new power. What if it were a 3? Add 1 to the power, divide by the new power. What if it were an e? Add 1 to the power, divide by the new power. Okay? And this one we've already talked about. The integral of e to the x dx is e to the x. I put a plus c just because it's kind of like a formula. But e to the x goes to e to the x. And so this one here is simply just 7 e to the x. And we're going from 0 to 1, and there you go. You actually just integrated. You just did it. And so now I'm going to plug in the 1 wherever you see an x, and that's going to be right here. So that's 3 to the 1, or 3 times 1 to the e plus 1 power. Very, very strange. I mean, you'll never do this again. Literally, I've never seen this in my math career except for this problem. And that's okay. It's fine. It's just weird. Oops, that's a minus. And then I'm going to plug in the 0 where we see an x. So 3 times 0, power e plus 1, e plus 1. Getting a little sloppy there. And then 7 e to the 0. So 1 to any power is itself. And so we have 3 in e plus 1. We have a 7 e to the 1, or just e. And then here's 0 times anything is 0, and e to the 0 is a 1. And so essentially that negative sign is going to distribute, make a negative 7. And there you go. That's it. You're done. You're done with that problem. That was it. So a little weird, but in the end, it was really not too bad. Now, this is weird. It says 54050, I think, but then I've got this 3, and then I got question marks, and I don't know. It's kind of weird. So if you see a 3 or a 4 on your homework or whatever, I don't really know if it's supposed to be there or not, but we're just doing it. Sorry. Start over. Okay, here we go. So then pi over 4 to pi over 3 of cosecant t times cotangent t dt. All right. Now this is a big time integral. But it's not too bad. It takes us a little bit of thinking. I'm okay with this kind of thing. This is good. Hard problems are not bad problems, okay? I think they're fruitless problems are bad problems. This one actually is good. You're going to see this again. This is good thinking. This is good strategy. Okay. What am I supposed to do with this? Now, could I go to, say, some kind of a formula book? Couldn't I look around and maybe find something that matches that thing? Perhaps. Couldn't I use the internet? Perhaps. I don't want you to. I want to think about this here. Generally, these questions are much easier because they put them in secants and tangents. Secants and tangents are much, much better, in my opinion. And so I'm going to do a little bit of pre-Cal, early Cal 1 reminder stuff. I'm not going to do this problem yet. I'm going to do my own problem. Let's just say I had the integral of a secant tangent. I'll put some thetas just because it's fun. So I think that this will be a little easier, and it's very related, and then we'll come back to it and do this problem. Notice cosecant, cotangent, secant, and tangent. It's like the same problem just without the cos. Now, I'm looking for something that will integrate to, something that will be a derivative equal to this stuff. So basically, I'm looking for something here that when I take a derivative, it will equal secant tangent. Okay, so what was the original? that made that happen? Okay, that's I guess the question. And I'm going to remind you because I'm waiting. I'm waiting. What's the answer? This is a recording, obviously, so I can't really wait. And so the answer is actually secant of theta. So the derivative of secant is secant tangent. So that was definitely taught back earlier in this class, and I probably made a big point about it because it's a big-time question. That's actually a very important question there for derivatives. Well, the thing is that we're going backwards. We're integrating, right? And so integrating, we're saying this was the derivative. Now I want to find the original antiderivative stuff, right? Okay, and so what would be the answer in this particular case? I would have said that the answer is secant. I don't know why I keep putting more boxes. The answer would be secant. I don't know, plus c or whatever the heck, but secant. Okay, cool. So we're going backwards. Now, we're going back to here. I'm saying that we had something derivative. It's a prime, and it's equal to cosecant cotangent. See, isn't that the coolest way to write it? Right? CSCTCOTT DT. Whatever. So what was the thing that we had to find the derivative of this one? And so, yes, you guessed it. It's cosecant of t. Oh my goodness. Kinda. It's a negative cosecant. And that's why I like to do the secant tangent first, because they retain their signs. Here, whenever you're taking a derivative or integral with a cosecant or a cotangent, got to make it a negative. Got to make it a negative. And so it's the same way here. I'm basically now saying that my integral here is a negative cosecant of t from the pi over 4 to the pi over 3. So I'm going to plug in the pi over 3, plug in the pi over 4. Two negatives make a positive, because there's always a minus sign between them. All right, unit circle, go. This is 1 over sine, right? 1 over sine of pi over 3. And then I got 1 over sine of the pi over 4. And so then we got, that's 60 degrees. Sine of that would be, what, square root 3 over 2? And, of course, any 45 will be a square root 2 over 2. And that's your answer. If you want to make it look a little bit more pretty, you could do this. And everyone would be so happy for you. Couldn't you get a common denominator with the square root 6 or something like that? And then you rationalize it and all that stuff? Sure. Or you can just keep on moving. 53009. Let's keep going. I got g of x is equal to integral 0 to x of the square root of t plus t cubed dt. And my g prime of x is what they're looking for. This was the identical same first problem that we did earlier. Okay. Now, I can go through all the steps again, and I have them here on my notes. But honestly, in reality, I think I should just tell you the answer, because it's not that bad. It's right here, but you're using the x's. There it is. You're done. I'm serious. Now, what I want to do, though, is a little bit of a cautionary tale. That's good for this problem. It's not good enough always, okay? What you will want to do is understand that this is a u and all that stuff, and what we want to do is take the derivative of that right here. Okay? So this is the thing right here. I want to take a derivative of that and multiply it right here. So looking at the x, I'm going to say, what's a derivative of x? And you're going to reply it's a 1, and that's correct. 1 times all this stuff is the actual answer. So we did this actually on the very first problem as well. If you remember, we took the derivative of e to the x, we put an e to the x out there, etc., etc. But I skipped all the nonsense, and I went right to the answer, and that's what you should be doing. This is what we're actually doing here, because the derivative of an integral cancels each other out, and you get back to what you had, but just make sure that there might have been a portion of something left over. All right, more hand-holding. So we got integral from 0 to x, f of t dt, and I love the hand-holding problems so much. They're my favorite ever. I'm sorry, I'm just making it a little too unbearable, perhaps. This goes all the way to 6. That's a 3, 4, 5, 6, good enough. And it goes up until 3, 2, 3, good enough. And then that's ending at a 7. All right. This is just a phenomenal problem. Everybody likes doing this problem. So g of 0 is equal to 0. That's correct. You start at 0. They say find the area from here to here. Here, you're plugging in that. Or, I'm sorry, you're plugging in that. There you go. Yeah, so from 0 to 0. Nothing at all. Okay, so g of 1, you're saying integral from 0 to 1 of this thing. Well, here's your 1, and you can notice right here, we got a little triangle action. Woohoo! So, I have, well, I don't really care what that's going to be. I'm just going to say it's a triangle. And so then I've got a 1 base, a 1 height, and times half. Okay. G of 2. I'm going from 0 to 2 now. Blah, blah, blah. Well, 0 to 2, we got this guy right here. And what actually happens here is kind of interesting. We got a positive half, and then we got this negative area on the bottom. Negative. So we got a positive 0.5 like we had last time. And then we're going to add a negative half. And, yeah, they cancel, make a 0. Kind of weird. When you go g of 3, again, 0 to 3, you can see the pattern here. I'm basically taking what I had previously and adding something else to it. And so here, I've got all this right there to add in. That's still a negative area. It's a negative amount. And you just keep on going. 5, 3, 0, 1, 3. Okay, I've got f of x is equal to integral of x to 0 of the square root of 2 plus secant of 7t dt. And they give you a hint. I almost don't want to give you the hint. But I'll give you the hint. It just takes more time for me to write it than it is to explain it. Though, yeah, I'll probably sit there and explain it forever because I'm a fairly verbose person. Man. All right. Great job. Thank you for that hint. Okay, here's the hint. So, we have our original integral here. Sorry, I messed up. I was looking the wrong line. That's an x and that's a 0. You got your original integral right here. You can flip the limits and make a negative in the front. And so guess what you're going to do? You're going to do just that. Step 1, follow the hint. Woohoo! Man, that was so fun. Now what? It's the same as that other problem. It's not hard. They want f prime of x is equal to something. And so what we're going to do is say, oh, well, the derivative and the integral cancel. And yes, indeed, they do. And so you got the square root of 2 plus secant of 7t. So that's always fun. We like that a lot. And then I have to multiply by the derivative of the x. So what's the derivative of x? It's a 1. And so there's your answer. You're done. That was it. You skipped all of that nonsense. But nonsense you can't get rid of. 53069. We got capital F, which is often like integral of something. X to x squared, e to the t squared dt. And I guess they want little f is what's going on. And so what they're trying to say is, what's the derivative? Let me just give you a formula. So capital F prime of x is equal to a lowercase f. If you had your integral of lowercase f dx, you get a capital F plus c. In a way here, what we're used to is f, f prime, f double prime, f triple prime, and whatever. Well, to go and integrate, we have a capital letter. Now, how do you integrate again? You make it a capital letter. No, I'm just playing. No, I have no clue what you do. You just stare at it. So, so how do we find our derivative? They're just saying this whole thing here, derivative. And so we're going to end up with our original, essentially, and with our derivatives of that stuff there. It's not that hard. Okay, it's not that hard. And so, let's go through this. It'll be okay. We can do this problem, okay? Here we go. I'm just looking at what they're doing here. Yeah, okay. What they are doing. That's me, by the way, what I'm doing, I guess. So I split up the integral like this, and that's nice. And then I said, oh, remember the last problem, we can flip it. Okay, cool. Okay. And so now, what do we do? Well, I'm just going to do what I always do. I'm going to say this right here is my answer. E to the t squared then times x prime. And put a negative, and then there's a plus sign here, so I do this guy here. So that'd be e to the t. So this is my derivative, by the way, at this point. This is derivative. So I have my integral, now I'm just finding my derivative. I got my original, and then what's my derivative of this guy is going to be a 2x. Notice that there. Hold on. I'm trying to be better. X squared prime. Okay. Whew. All right. We can do this. I'm trying to be better. I'm trying so hard to be a better teacher to you. There we go. Very nice. Here's the problem. Whoa. Here's the problem. It's not right. And I don't even think that's good math, technically, but it doesn't really matter for our purposes. The reason why it's not good is because we have t's and x's mixed up. So here in this case, we're going to have to use, this was my t, x, u, whatever. You're plugging it in. And so what you actually get there is going to be an x instead. I guess you could say times 1 if you really care to. But here in this case, this is my t, x, u, whatever. I don't know. You plug it in here. And so what you actually get is x squared still times the 2x. And notice that we have only x's now, which is nice. And so then we got a 2x. And then you can notice the square squared will actually make a 4 power in the end. And that's your answer. Okay. We did that thing so nifty. And the last question of this section. We got the limit as n goes to infinity because they can't let it go. They are so sure that you need to know what fuel injection and automatic transmissions and timing chains all are required for radiators before you just press the gas and the brake, and that's them. This is a good thing for everyone to learn, just not first. At this point, I'm going to start to now try to take it in a better light because they're going to finally let me have the keys to the car. I can go and do my thing, okay? Now, this is a difficult problem. This is not just something that we can just brush off and call it a day here. Actually, I do have one other problem after this. My bad. It's not your last problem. It's just kind of like I scrunched two things together, I guess. So find the Riemann sum. Well, essentially, this is going to be an integral. And that's actually what they're wanting you to do. They're wanting to say that this is equal to an integral of blah, blah, blah. And that's a good thing. We want that. We want to be able to convert these whenever they give us strange things. And so how do I go about actually converting this stuff? That's going to be the question here. So I'm going to say the limit, summation, doesn't change, doesn't matter, of, and I'm going to make something up. This is kind of weird. I'm going to pull an n out of both of these and make 1 minus 0 over n times, and now we got I cubed, n cubed, and then plus I over n. I'm sorry, my original had a square there. I'm sorry. My original had a square. I'm sorry. Go back and add it, because this is supposed to be an n here. My bad, my bad. Okay, so that was an n squared. Always watch to the end. Okay, so that's what I'm doing. I'm pulling out an n, and where is this 1 minus 0 coming from? It's coming from thin air, because I got to put something in the numerator. Might as well make it something nifty and cool, and oh my gosh, I've seen that before. This is a delta x, basically. That's a delta x. In a way, I'm trying to say I got my delta x, and this is going to be my f of x sub i's, and all that stuff, and all this right here, guess what that is? Integral dx f of x. And so that's really what it's going to end up being. You see it? Now we just got to be able to put it all together in the correct format. So here we go. Integral. This is equal to, right here, equal to integral of. And right here, this is I over n, both cubed. And so I'm actually seeing this as x cubed. In a way here, I have my my x sub I is 0 plus delta xi. There was a formula just like this earlier. You don't need the 0. Why do I have a 0? It's because there's a 0 right there. So, okay. And so that makes up the 1 over n, whatever, with an I guess. Okay, so 1 over n, x over n. We got 3 of those, right? So this is I, not x. Sorry. There we go. I over n. And so then I'm basically just saying mine's cubed. And so there you go. It's x cubed. And then here we got x. And then it's a dx. Whew. Now we can do this thing. Oh, and it's 0 to 1, by the way, because they had told us 0 to 1. Okay, we got this thing now. Add 1 to the power. Divide by the new power. From 0 to 1. And so then we got 1/4 plus 1/2, and then minus 0 essentially. And so that's going to be a 3/4, and we're done with that problem. So all of this craziness here ends up just being a simple 3/4. I don't make this stuff up. I just do it. And so this now is my last problem, finally. And it's got to be somewhat ridiculous, of course. We got e to the x, and we have an a area that it goes until a. We got e to the x. Again, that's a terrible, that is not what e to the x looks like. Not to scale, not to scale. And then I got something a little bit further out at b. This is going to be my b area here. And they say that b is equal to 2a. Find little b. Is that literally all they say? Wow. Wow. What do I do? So from this here, I can say that my area A is equal to the integral from 0 to little a of e to the x dx. And from here, I can say that my big B is going to be an area from 0 to b, e to the x dx. Well, what's your integral of e to the x? Is e to the x. And what's your integral of e to the x? It's e to the x. And then I plug in the a, and then I plug in the 0. Plugging in the 0 is very important here, because e to the 0 is a 1. Same thing here. And so this is a, and this is b. Now they said b equals 2a. And so I'm going to plug those in just as I'm supposed to. If that looks like a 9, I'm very sorry. It's just an A. Distribute, so e to the b minus 1 is equal to 2e to the a minus 2. Okay. And I want to solve for b. What was that? Yeah, b. They want to get b by itself. So they want this b by itself. I'm going to add 1 to both sides, if you don't mind. And no, it's a minus 1. To get b by itself, I'm going to ln both sides. Cancel. So b is equal to ln of 2e to the a minus 1. And that is literally the answer that you type in to WebAssign. That's it. I think we're finally out of Math Prison, and thankfully. So off we go to bigger and better problems. Thank you very much, and have a great day.